Welcome. In this video, we're going to start our discussion on exponential functions, and we're going to do this by introducing the paper tear problem. We're going to start with a single piece of notebook paper. We're going to tear the sheet in half and stack the pieces, then repeat this over and over again, making sure to stack the pieces each time. We're then, for part A, going to make a table that shows the number of pieces of paper here for Y remaining after X tears. So 0 tears, 1, and we may as well fill in this top line, 2, 3, 4. So we're going to repeat this and tear the paper 4 times. So since instructions can sometimes be tricky to understand by just reading them or hearing someone read them to you, I'm going to show you how to do this. So right here I have a sheet of coral paper, and I'm going to cut it in half. And to get a good half, I'm going to fold it first. And I know this is called the paper tear problem, but I don't think I could do a very straight tear. So here's the first fold in half. Open it back up, and now I can cut along this fold. Oh, before I cut though, when we have 0 tears, there is 1 sheet of paper. So under x equals 0 on your table, fill in the number 1. And now let's cut. When we've torn the paper or cut the paper once, we now have 2 sheets of paper. So fill in the number 2 on your table. Now let's stack these and do it again. So I'm going to fold it just so I know exactly where my halves are. Open them up, making sure these papers are still stacked on top of one another, and then cut down the middle. There we are. And now how many pieces of paper do I have? 1, 2, 3, 4 sheets of paper. So under 2 tears, you should have the number 4 written down because we now have 4 sheets of paper. Let's do this a third time. So here they are all neatly stacked. I'm going to fold just to get an idea of where I'm cutting. Open them up, and then along that crease, I'm going to continue to cut. So with 3 tears, we have 1, 2, 3, 4, 5, 6, 7, 8 pieces of paper. 8 pieces of paper with 3 tears. Fill in on your table y equals 8 for the x equals 3 spot. Finally, let's do this a 4th time, and I'm just kind of going to estimate where the half is here. I'm not going to fold it in half, especially since my paper's looking kind of crooked right now anyways. So here we go, cutting this in what I think is half. And now without counting these, I had a stack of 8, and now I have 2 stacks of 8. So I have 16 total sheets of paper, but if you must see them counted, here's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and 16 pieces of paper. You now should have your table filled in, and we can continue with the rest of this discussion. Your table should match this table that I have here on the screen. Now let's look for a pattern in this table that completes the following sentence. When I increase the input by 1, the output, what? When we go from 0 to 1, our output goes from 1 to 2. When we go from 1 to 2, our output goes from 2 to 4. What is happening here? Well, the output is doubling. 1 times 2 gives us this number. 2 times 2 is 4. 4 times 2 is 8. 8 times 2 is 16. Part C. Is this function from part A linear? And how do we know? Well, if the function is linear, we should be able to find the slope between any 2 sets of points, and that slope should be constant. So it should be the same number every time. So let's try the slope between 0, 1 and 1, 2. The slope here is 2 minus 1 over 1 minus 0, which is just 1. Now what about the slope between the next 2 points? That is between 1, 2 and 2, 4. Well, the slope between these points is equal to 4 minus 2 divided by 2 minus 1, which is just 2. Since these numbers are not the same, we know this function is not linear. Part D, find an equation for the function in part A. So the type of equation we're looking for is no longer going to be y equals mx plus b. This is linear. And we're no longer working with linear functions. What we're looking for is something that looks like y equals a b to the x power. This is exponential. And it's unfortunate that they both use a b. That's why I used a capital B for exponential, but we can just write a little b. So let's look at what everything means. First, let's start with, what is a? Well, let x equal 0. When x equals 0, we have y equals a times b to the 0 power. Any number to the 0 power is just 1, so this is a times 1. So y is equal to a. This tells me that a is the initial value, also known as a starting point. Okay, so what about b? B is our rate of growth or decay. In this case, since our outputs are increasing, we know we're growing. Furthermore, we know our outputs are being doubled, so b has to equal 2. All that said, this tells me that our equation in the form of y equals a times b to the x is just y equals 1 times 2 to the x, which is just 1 times 2 to the x. Part E. Let's check that the values in our table match the values in our equation and show these checks. So first, let's rewrite our table. So that's the table values recreated in our introductory activity. Let's go ahead and check them against this equation that we came up with. So when x equals 0, y equals 2 to the 0 power, which is just 1. When x equals 1, y equals 2 to the 1 power, which is just 2. Please try the last 3 entries on your own independently by pausing this video. And as I have gotten in the habit of saying, I can't force anyone to pause this video and try the problems, but it is in your best interest to actually try the problems and understand how to do them and the underlying concepts. So please pause the video and try these 3. When x equals 0, y equals 1, which matches our table. When x equals 1, y equals 2, which also matches. And you should have matched at the last 3 ordered pairs. So when x is 2, y is 4. When x is 3, y is 8. When x is 4, y is 16. Now let's use our equation to determine the number of pieces we'd have after the 20th tear. In this case, x equals 20. And 2 to the 20th is a rather large number. It's 1,048,576. That's how many pieces of paper we would have after the 20th tear.